In Chapter 3, we were first introduced to the concept of skew as a way to talk about not so much the spread of a data, but does it tend to be pulled in one direction versus the other. And here in Chapter 4, we'll talk a little bit more about it and think about ways that we could potentially measure it or calculate how much skew we have. So remembering, what we're really discussing here is a relative sense of our distribution and where the data tends to be, and we're thinking about again, a zero skew is that nice symmetrical value, or sorry, symmetrical distribution where the middle of the data is represented both by the mean and the median. Right? If this data is completely symmetrical, half the values are below and half the values are above, and those deviations are going to cancel out, and the mean is going to be right there in the middle. Right? So one of the ways, if I could spell it right, the median equal to the mean is that sense of being right in the middle. Now, not all distributions are nice and clean and symmetrical like this, and sometimes we'll have, a lot of times we'll see bimodal distributions, right? So this is a single or unimodal, right? Uni being one. We can have bimodal, where we kind of have two peaks in terms of the distribution of the data. So a lot of times we refer to skew or calculate skew when we're talking about a unimodal distribution. And so, classically, what we just had written was kind of the zero skew, or close to zero, and but we can have positively skewed where there's more data out here, or I had space for this, but on the flip side, kind of a data on the lower end that's pulling it the mean lower. Okay, so again, both the mean and the median matched up in the zero skew. When we have this type of a situation, often what we'll have, so the positively skewed, we'll have a median, and we'll have the mean somewhere over here. Right? Because those higher values are going to pull the mean higher without actually changing where that median is. And vice versa, the mean in a negative skew, you'll see the mean below the median. So let's look at some actual data here. This is the data we used when thinking about the percentiles. And remember, of course, the median being that center percentile, or the 50th percentile, there's the second quartile. And so what we have here is again, it's 40 observations. So the center of it, or it's 39 for ease of computation. We have 39 observations, so 19 are below and 19 are above. And if we simply calculate the mean, I have calculated a few more things, but the mean here in this data set is 38.15. So right there, we can assume that our skew is going to be what? Well, we have a mean greater than the median, and so we're going to be here with a positive skew, right, as opposed to the negative skew. And in fact, so what would be driving this? And luckily we have the data nice and sorted here. We can see that down here on the bottom we have a very large value, right? So maybe this is, it would be hard to be income, but we have some people making $2,000, and we have some people making in the 30s, and then we have somebody making $356,000 or something like that. Okay, so we have one value that's way out on the extreme. So this is kind of an extreme case of this scenario where it's really just one value pulling it higher, although some of these other values maybe strain it a little bit as well. So actually, and we can turn and look directly at the histogram to get a bit better feel for this as well. So let me drag this out here, and we can see the histogram of this data. Now we only have 40 observations, so it's not nice and smooth. But we can get a feel of that positive skew, and again driven in this case by this single observation way out here on the end. But the concept remains the same, is that we have large values that are pulling that mean higher than the median, and so we no longer have this nice symmetrical display. And we can again, so we can look at it visually. We can also go ahead and calculate it, and so your book outlines two different measures of skew, or two different calculations. One of which being the Pearson's coefficient of skewness, and then the other one is a software measure. And I'm not going to have you recreate the software measure, but I do want you to know that it's there and that it is different than what we're going to calculate here. But the concept remains the same, and they're trying to accomplish the same thing. So the Pearson's measure is simply SK is 3 times X bar minus the median. I run out of space. Just abbreviate that MED. And then divided by S, where S is the standard deviation, right? And X bar is the mean. So S and X bar tells us we're talking in sample methods here, but we could translate this to with a population as well, with mu and sigma. But the essence here is X bar minus the median, right? And so what does that really? So if we look at this equation, the standard deviation is always going to be positive. 3 is always going to be positive. And this is always positive. This is always positive. And so where we end up as far as positive or negative all relates to whether the mean is greater or less than the median. Okay, and so and that fits right in line with our pictures. Right, I've got it covered up here, but with the if we have a positive skew, the mean is greater than the median. Negative skew, vice versa. Okay, and so we can actually calculate an exact result from our equation here, and so it will be, let's just pick a color here. So 3 times 38, put it in brackets here, 38.15 minus the median, which is 30, and then we divide by the standard deviation. We'll just call that 57. So we can think about what's happening here by, sorry about that for here the phone. We can think about what's going on here, in that we want to keep it relative to the standard deviation. So yes, we want to know whether the mean is bigger than the median, but it should factor in the standard deviation. So how spread out is this data in general? And here, so we're really measuring the distance between the mean and the median relative to the standard deviation. And this concept of comparing things to the standard deviation is going to pop up again and again as we go throughout the class. A way to kind of bring it into context, right? So if we have data that's all, bunched in there from 0 to 10, and we have, a mean that is 4 more than the median, that might be really large, right? If you have a mean that is 4 whole values above the median, and your data only jumps around, in general between 0 and 10, that's a different skew than if you have, let's say you have a mean that is 20 more than the median, but we're talking over, a range from 0 to 1,000, then that difference of 20 is not as big of a factor. And so that's what the standard deviation is trying to take into account, putting it into context. And so this becomes, so it's 3 times 0.1429, becomes 0.429, we'll call it. And so it's positive. And so we do have a positive skew. Now this ends up not being you would consider it kind of weakly positive. And so skew can range from -3 to 3, and a value. So 0 is or right around 0. You know, if you're just a little bit off of 0, you would kind of consider that to have no skew. Kind of a rough feel is something above 1 or above 1.5, or I think the book even says, you know, there's kind of a 1.63 is sometimes thought of as like moderate skewness. And so anything below 1 for sure you would think it's not really that skewed. And even though we have this one value way out there, a difference of 8 in the mean isn't that large of a difference with such a high standard deviation. Now, again, this is just one measure of skew, and we could at some point plug it into the software method and see what that pops out. But in general, the two fall pretty closely to each other.